Hey Rock Buds, more rocks for you. I hope you enjoy it. Okay, here's an interesting rock. It's kind of dark. It's got some light colored minerals in it. So our first question is that dark mineral biotite? And as you know, biotite, a nickel will scratch biotite. So, no, the nickel does not easily scratch this dark stuff. So that means this has got to be hornblende or pyroxene. Also, the white mineral, the lot of light mineral. What do you think the white mineral is? Right. Feldspar is almost always white when you see it in a rock. Now remember, with the mafic rocks like gabbro and diabase, which are igneous intrusive mafic rocks, remember that the white feldspar minerals or crystals were kind of raggedy looking, long stretched out, kind of raggedy. Do you see that here? I do not. I do not see it, but I do see this iron weathering rind. So what are we going to call this rock? Is it intermediate? It doesn't have biotite or much biotite in it. It's probably hornblende. Is it mafic? No, it's not mafic. I don't think it's mafic because the white feldspar does not have that lath-shaped or raggedy shape that I just talked about. So it's kind of in between an intermediate and a mafic rock. And we actually have a name for that. And we will call this hornblende gneiss. And most geologists, when they see a rock like this, they're they feel it's intermediate. They're gonna call it, or intermediate to mafic. They're gonna call it a biotite hornblende gneiss. But this stuff doesn't scratch, so we're gonna call this a hornblende gneiss. So, how do you tell biotite gneiss from hornblende gneiss? If your nickel will not scratch the black stuff, then you know it's not biotite. It's going to be hornblende. So you've got hornblende gneiss. How do you tell hornblende gneiss from, let's say, diabase or gabbro, or amphibolite, which is the metamorphic version of diabase, gabbro, and basalt? How do you tell it? Well, you look for the big lath-shaped or raggedy-shaped feldspar crystals. And this does not have them as far as I can tell. They're more like little dots. This is relatively fine-grained. It probably formed fairly deep. It's an igneous pluton. This material is an igneous pluton. So we're going to call this hornblende gneiss. It is found in the inner Piedmont, which was an island arc. It's found in the Carolina terrain, which was also an island arc, and it's found in the eastern Blue Ridge province, which was island arc plus ocean sediments. So that tells you right now that since all these island arcs were formed by subduction, that's where a lot of this hornblende gneiss comes from. But like I said before, most geologists would just clump it all together and call it biotite. Call the stuff that looked like this biotite hornblende gneiss. And this is probably an intermediate to mafic rock. Then I would say that the feldspar in here is probably sodium rich, mostly sodium, maybe some calcium rich, calcium feldspar in there. So, hornblende gneiss. Okay, here's our next rock. And you can obviously see that this here rock is made of a grayish colored fine matrix with embedded larger crystals in it. I say crystals, I should say embedded hunks of other rock. So is this an igneous rock? Well, you could be tricked into thinking that it's an igneous rock. But this is kind of a giveaway. This material right here, what does it look like? Does it look like dark mud? And that's what it is. So this rock has some dark mud clasts in it. Here's some more. So that probably tells you it's a sedimentary or a metasedimentary rock. So what are these hunks that are embedded in it? See, there's another of the mud hunks. If we decide it's a sedimentary or metasedimentary rock, the white, since these white hunks are white, I'm going to call them feldspar. And I also noticed that they're kind of angular. They're not terribly rounded and smoothed off the way that they would be if they'd spent a lot of time in a river. Obviously, this is a rock that was deposited by water, and I don't see any quartz. There's probably quartz in here somewhere, but not much. Maybe a little bit there. A lot of little mud hunks, a lot of feldspar, rough feldspar hunks. Okay, this abundance of feldspar tells us something. First, it tells us that this material, the mud and the pebbly, rough-cut pebbles material, did not spend a lot of time in a stream. Because if this material had spent a lot of time in a stream, the feldspar pieces would be well-rounded, and they would also be not that many of them here as well, because feldspar will erode out or weather out of in a stream much more quickly than quartz. We also know that from this that the source rock was feldspar rich. Okay, so that's telling us that this is a sedimentary or metasedimentary rock that was deposited quickly. And so, based on that information, I'm going to call this a turbidite deposit. And specifically, I'm going to call it turbidite sandstone. Let me tell you how this rock forms. This rock forms when material of several sizes, including feldspar, gets washed into a basin quickly. So that tells us that it could have been deposited in a Rodinia rift basin, which in this case it was. This rock also forms where the continental shelf in the ocean, which is the relatively shallow part of the ocean surrounding the continents, drops off into a slope called the continental slope. And this material gets dumped down that slope, all mixed together size-wise. And that's one of the keys here. It's all mixed together size-wise, different sizes of material. Another place this kind of rock can form is in what we call subduction melanges, and that's where a subducting island arc or microcontinent subducting beneath a continent pushes up all kinds of rock material, mud and rock like a bulldozer, and piles it on top of each other and rolls it and tumbles it. Now, some geologists would call this a meta-graywacke or graywacke, and it is a meta-sedimentary rock. This rock comes from the western Blue Ridge province, which we know is the remains of the Rodinia rift basins that formed prior to Rodinia's rifting. So we know this is a turbidite deposit. In other words, it's formed in turbidity currents, and turbidity currents happen when materials wash very quickly down into a basin and doesn't spend a lot of time in a stream, so that the feldspar remains unweathered out, and also it still has kind of angular edges. Some geologists will call this meta-graywacke, but I make a distinction between the two, between meta-graywacke and this rock, which I call turbidite sandstone. And it's just a matter of relating to the size of the embedded hunks. For me, if the pieces of rock, whether they be quartz or feldspar or shale, mud, whatever you want to call it, if they're about the size of Abe Lincoln's head, then I call this turbidite sandstone. And the reason I do this is because the same material in the Great Smoky Mountains National Park is just called sandstone by geologists, but sandstone means something different to me. Sandstone, when you say sandstone, to me it means a rock that has quartz, mostly quartz grains, and they're small and they're equigranular. That means they're all about the same size. This definitely is not that. This is like a muffin with raisins in it, whereas regular sandstone is just like a piece of bread. So if you get this muffin arrangement and the clasts or rock hunks are about the size of Abe's head plus or minus, I call it turbidite sandstone. But if they are about the size of Abe's ear, then I call it metagraywacke or graywacke. Hope that's not too confusing. And here again, this material is from the Western Blue Ridge Province. The Western Blue Ridge Province runs northeast to southwest in the eastern United States, just east of the Valley and Ridge Province. And it is the remnants of rift basins that formed when Rodinia supercontinent rifted apart around 750 to 550 million years ago. And also there's a lot of volcanic material, mostly basaltic, that erupted as the rifting took place. So turbidite sandstone with a lot of feldspar hunks in it and not hardly any quartz hunks in it. Okay, our next rock. This is a kind of a weird looking rock. But look at this. What does this look like? If you had to say what mineral this is, what would you say? And there's a lot of it. Matter of fact, this whole rock is made of the same stuff. Oh, here's another area. So this is one big hunk of quartz with a lot of crystals in it, a lot of quartz crystals. Now, why isn't this white stuff? Why is it not feldspar? Well, because I don't see the other minerals, feldspar and biotite and that sort of thing, that would make this an igneous or metamorphic igneous rock or a metamorphic equivalent of an igneous rock. So this is what I'm going to call quartz vein rock with quartz crystals in it. And these are small quartz crystals. Somehow I want to call these hen's teeth crystals, which hens don't have teeth. And those are much larger than the teeth on a hen. So we can pretty easily tell this has a lot of little quartz crystals in it. So how does this rock form? Why does it form like this? If you go down to the creek, if you're in the Piedmont region of the eastern United States, or either the mountains too, and you go down to the creek, you're going to find a lot of quartz vein rock. Quartz vein rock doesn't have the crystals like this, usually. It just has amorphous crystals, which means you can't really see any crystals. It's just a hunk of quartz. So how does quartz vein rock form, and how is this different from quartz vein rock? Well, quartz vein rock forms in veins. You have metamorphic pushing and shoving that'll open up a crack in a host rock like granite, gneiss, sandstone, anything. And water, which is laden with, has a quartz or silica in solution. Remember, quartz is one of the minerals that's ubiquitous all over the world. Quartz, iron, and calcite are just in water everywhere. Abundant. Quartz may be the most abundant. Yeah, maybe quartz and iron are tied. Anyway, the water laden with this quartz gets into the crack and deposits the quartz in a very thin line. The crack opens up, more quartz is laid down against the first line, and after a while you have a long vein of quartz, amorphous quartz. Okay, this is quartz vein rock, but it formed a little differently. Not only did the cracks in the rock open up just a little bit so quartz would fill them, but they opened up a good bit so that there were pores and spaces in the rock, big cracks that very likely were full of mud, quartz-rich mud, water and quartz-rich mud, and there was plenty of quartz material and plenty of space, or enough space for these quartz crystals to grow. If there's space in the crack, the quartz crystals will grow, and there was just enough to make these little quartz crystals. Okay, so what determines whether you get the really small cracks that get bigger and bigger and you get the amorphous quartz vein, or you get a quartz vein with these crystals in it? Well, I can tell you this, that this rock, this hunk of quartz with its crystals, came from a major fault zone here in the eastern United States. This hunk of quartz that was deposited in a major fault that separates the inner Piedmont geologic terrain from what we call the Cat Square terrain. The Cat Square terrain was an ocean basin that formed way up north in association with the Carolina terrain, which then slid down here to Georgia, South Carolina, and North Carolina along several fault zones, including the Brevard Fault Zone. And the Brindle Creek Fault is the fault that separates the inner Piedmont from the Cat Square terrain. And you often find this kind of deposits where there's quartz veins and quartz crystals forming where these major faults occur. If you go to Arkansas, look at a geologic map of Arkansas, you'll see it's riddled with faults. And that's why Arkansas is one of the quartz crystal and amethyst crystal capitals of the world, because these faults zones have enough space in them for crystals to form along with all the quartz. Okay, here we got a rock, the last rock. Let's just have a look at it. See a little bit of layering there. That looks like quartz, layers of quartz vein kind of layers. When you have quartz veins like that hints that you've got a metamorphic rock. That's not all we have. We have the quartz veins. Let's see. Let's find there's a, let's look at this. See right in here? I don't know if that's in focus or not, but that's pretty fine. If there are mineral grains in there, they're very small and they're equigranular. So this is I'd call this sandstone, but it's got these quartz veins in it, and it's got all this dark stuff in it. So why don't we call it quartzite, since it looks like kind of like a sandstone type of rock. It's easy for you to say, Papa, because you know what it is. Well, I already figured it out. So let's just call this quartzite, but it's not just regular quartzite. What's this black stuff? Well, I tried to see if this would stick to a magnet, and it doesn't. I put hydrogen peroxide on it and it doesn't fizz. But my assumption is, since sandstone is a porous rock and can become mineralized, then we know that there are 3 minerals that very often get into sandstone and other rocks when mineralization occurs. We know it's quartz, and we have quartz in this rock. Iron and calcite. Well, if this black stuff is calcite, it should fizz, right? Well, I checked it and it doesn't fizz. So what does that leave? That leaves iron as the most likely candidate for this material that was mineralized into this reddish colored sandstone. And because the sandstone is kind of reddish, the quartzite is kind of reddish here, where the black stuff isn't, then that tells me that there is iron, a lot of iron in here. This is not magnetite. How do I know? How am I pretty sure it's not magnetite, which is a form of iron? Because it doesn't stick up to a magnet. So I'm going to call it hematite, which is the other form of, and another form of iron. There are several forms, but hematite and magnetite are the main ones. So, yeah. So we know it's a metamorphic rock, metamorphic sandstone that's been mineralized with a lot of iron. So let's call it iron-rich quartzite. So how does something like this form? Well, you have sand. Let's say you have sand beaches, and subduction occurs near those sand beaches. Volcanic action erupts all of this iron-rich material that gets into the water, and it gets the iron material by the processes of subduction and crashing, continental crashing, gets mineralized into the sand. And then metamorphism pushes all of it into a quartzite. This is a product of the inner Piedmont geologic terrain, which, as we know, was a volcanic island chain that formed during the Taconic or Taconian orogeny, which occurred about 480 million years ago, plus or minus. So that would provide the subduction and mineralization, the volcanic activity that would have produced the iron, and then later on, this island chain was smashed into the continent, and that would provide the continental tectonic smashing and crashing that would have mineralized this sandstone and metamorphosed it, giving rise to this iron and these quartz veins. Zones of quartz. Okay, guys, thanks for watching. Happy rock hunting. Pop out.